All right. Hey everyone. So today, as you might be able to notice, I am actually in my office because the internet at my house died. So I had to come here. So I am on campus, but not in the lecture hall. Next week, we'll be back to normal in person. So, okay. So today's topic is vision and language. But before we start with the lecture, I wanted to go over the answers to the midterm exam. So I'm going to start by doing that, and then get through as much of the vision and language stuff as I can before class ends. All right, so we have just started grading your exams. I know things got a little slow because I fell sick, but are making progress now. And hopefully you'll get those grades back within a week or so. Also, logistically, the homework will go out today by the end of the day and will be due in early May. That's your last homework, and then you just have your final report after that. All right, so let's go over this midterm. So the first problem was about this kind of zero-shot setting where you had multilingual summarization. So specifically, you had only English summarization data. So you had the CNN Daily Mail data set. So you had large-scale English summarization data. And for evaluation, you had 1,000 document summary pairs that were written in Thai. So you were not allowed to use any of this data for training. It was purely for evaluation. So the problem was basically saying, oh, the audio is echoing. Not sure why that is. Is it still happening? You can let me know in the chat. Okay, great. All right, so let's get to the question. So basically, it was asking you, given a large multilingual language model and zero training data in Thai, can you still learn a Thai summarization system? So in question 1.1, this was basically checking your understanding of tokenization across different languages. So Gabby fine-tunes MT5 on the CNN Daily Mail dataset. This is in English. And then she evaluates her model at test time by doing decoding using beam search and then computing the Rouge 2 score, which is measuring bigram overlap against the ground truth summaries. So the critical sentence of this problem was that tokenization for this evaluation was done by splitting on white space. And so this seemed to work fine for CNN Daily Mail's test set, which is in English. The Rouge score was 35. But on her Thai data, it was only 1.8. But the question mentions that when she qualitatively looked at her model outputs, they were actually good. They were in Thai and looked reasonably good. So the 1.8 Rouge score was not actually evaluating how well the model was doing. Okay, so the reason why this is the case is that Thai is a language where white space tokenization is not a viable solution. And in fact, white space is not used to tokenize words in Thai. So that's why if you tokenize via white space tokenization, your Rouge score is going to be meaningless. And so that was the simple answer to this problem. So the next question asks you to come up with a way to address this issue without using anything external from what was mentioned in the problem statement. So we had quite a set of diverse responses here, but what we wanted you to realize was that MT5, the pre-trained model, already has its own tokenizer which works across many different languages. And note that it was pre-trained on Thai in addition to 100 other languages. So MT5 has its own subword tokenization, which you could have read about if you read through the paper. And a simple fix for this solution is simply to re-tokenize the outputs of this summarization system using MT5's tokenizer instead of the white space tokenizer. So this would enable you to get a much more meaningful Rouge score, because now you're actually doing tokenization and not just using this white space rule, which doesn't work across all languages. So that was the answer that we expected there. And now the next two subparts here focus on this phenomenon that is commonly experienced in these multilingual zero-shot settings, where whatever language you fine-tune on, the output from your model, even when you switch languages at test time, will include some text in that original language. Oh, I see a question. Would character level tokenization work for this sort of a case? Yes, if you had a character level tokenizer for Thai, you could certainly apply it and compute the Rouge score based off of it. But note that the problem said that you must not use any external resources. So you had to describe how you would get such a tokenizer. And that's why using the MT5 tokenizer is a way to get around that restriction. But you would certainly get partial credit for mentioning that. All right, so let's get back to this problem. Here, Gabby is trying to reduce the amount of English that is in her outputs when she gives the model Thai documents as input. And the problem says she decides to use prompt tuning instead of full model fine-tuning on the English CNN Daily Mail data set. And she notices that with prompt tuning, there's significantly less English being produced than with model tuning. So that means the prompt tuning approach is producing more Thai and less English. And the question is asking why you think this could be the case. So here, the reason is really one of the reasons we discussed for why methods like prompt tuning and prefix tuning and so on are pretty robust. Because with full model tuning, the entire MT5 parameters are being adjusted to optimize for the performance on this English CNN Daily Mail dataset. So it's very likely that at some point during this fine-tuning process, the model kind of overfits to English because it's just seeing English documents and English summaries, and it forgets how to deal with other languages. But in prompt tuning, note that the vast majority of parameters in this MT5 model are not touched. And so it still retains all that knowledge about how to generate tokens in different languages. It's just a very small sequence of embeddings that is prepended to the input that is learned. And so in prompt tuning, there's much less of a chance that the model would overfit to English and forget how to produce Thai tokens. So that is the answer that we were going for. Yeah, I see another question about 1.2. As a tokenizer is based on sentence piece, if we mentioned sentence piece, would that work as an answer? To get full credit, you would have to have mentioned that you use the MT5 tokenizer, the one that was already estimated on their pre-training data. But you would certainly get partial credit for mentioning sentence piece as a tokenizer. All right, and finally, question 1.4, was basically testing whether you could read through the MT5 paper. The answer was in there. Or at least one possible solution was in there. So here it says, she tried prompt tuning and it helped, but there was still English being produced. So is there any other way she could proceed to further reduce the amount of English that are produced in the Thai summaries? And here we allowed external data sets, but no new models. So one easy solution, which was described in the MT5 paper, is to alternate between batches of the English CNN Daily Mail and normal language modeling batches that are in Thai. So you could have these kinds of competing objectives where the model is learning to be a good English summarizer, but the model is also learning, it's being forced not to forget how to generate text in Thai. And so this kind of alternate batching where you are solving one task in one batch, like English summarization, and another task, Thai language modeling, in another batch is a really good solution for these kinds of problems. Can we use Spot? Yeah, that could also work as a solution for this. So Spot is a new research paper that could address this kind of thing, where instead of doing this alternating batches, you can do it in stages. So you can do first fine-tune on Thai language modeling, then fine-tune on English summarization or something like that. That would definitely be a viable answer as well. Not one that we covered in class, but still acceptable. All right, so let's go through problem 2 here. So problem 2 was a little less tricky. Here we had this task where you had 100,000 short stories and each of them are 2 paragraphs long. And you basically want to solve this problem where you want a classifier that can, given P1 and a candidate P2, can you decide whether or not the P2 is real or if it was generated by a model. And this obviously has some real world applications to things like, fake news detection and so on. So question 2.1 was basically a setup question. So if you're just given this data set with the real P1 and P2, and you're given a pre-trained GPT-2 model, how would you set up a data set and a classifier for this task? So the first thing you need to do is generate the P2 stars, the model generated paragraphs. And you should have said that you will do this by taking the pre-trained GPT-2 model, feeding in P1, the first paragraph, the ground truth paragraph, and then applying some decoding algorithm to generate P2. And so this could have been nucleus sampling, it could be beam search, or whatever. You should have said use some decoding algorithm to produce the P2. And now you actually have your full data set. So the next thing you would need to do is partition your data into train, validation, and test splits. And it would be good to apply some sort of filtering on the data to make sure that the model generated P2s are roughly of the same length as the real P2s to avoid any trivial solutions learned by your classifier. Then finally, you could train a model like BERT. You could fine-tune a model like BERT to, given P1 and a candidate P2, decide whether or not that is a real or a fake model-generated paragraph. So many possible options in these answers are acceptable. So of course we will grade accordingly, but those are the important features to touch on. And again, if you have any questions, put them in the YouTube chat. So question 2.2 was more interesting. So Isidora's able to build the classifier based on however you specified it above. And she wanted to use it to kind of implement this alternate decoding algorithm. So basically, to generate the next word, she is going to create V, where V is the size of the vocabulary, candidate sequences by taking the prefix, appending every word type in the prefix to this every word type in the vocabulary to this prefix one by one. So you're going to form V different candidate sequences. And then she's going to pass each of these V sequences through her classifier and then rank all the sequences by how real the classifier thinks the sequence is. So, and then she's going to choose to generate the word type associated with the candidate using whatever decoding strategy she wants. She could do like greedy decoding or sampling or whatever. So the question asks you to identify two issues with the method. One issue, which I think most people were able to figure out, is that this algorithm is hugely expensive. At every single time step, you have to rank V different candidates where V is the size of the vocabulary. This could be in the hundreds of thousands to millions. So this algorithm is just not practical at all for anyone to use. So setting aside the computational expense, another major issue is that the data set of the classifier and the way it's being used in this decoding algorithm, they're not the same kind of data. So remember that in this classifier, the classifier's input is always 2 paragraphs, and it has to decide whether the second one is real or not. But here, you're generating 1 word at a time. So you might start with no input at all, and then generate 1 token, and then you have a very short sequence, which the classifier has never seen before, right? These super short sequences are out of distribution for the classifier. So we don't know if it can give you good estimates of whether or not the text is real or not if the input is not exactly 2 paragraphs long. So that kind of distribution shift is another issue with this method. I'm sure there are many others, but these are the ones that we had written down. So we will assess other answers, and if they make sense, give you credit or partial credit. All right, I see no questions, so let's move forward. All right, so question 3 was a little trickier question about a transformer variant. So I told you should expect one of these, and yeah, this one was this kind of constrained attention, where the attention mechanism is only considering the first 128 key vectors when computing the query key dot product. And all of the other keys are automatically assigned an attention score of -infinity, which after applying a softmax will become 0. So one key misunderstanding of Ozzy is that in this sentence, it says Ozzy reasons that because a transformer's effective window size increases from layer to layer when using constrained attention masks, an Ozzy attention model with enough layers should theoretically be able to encode all tokens in an extremely long document. So we talked about in the previous midterm, the practice midterm, there was that problem about the trigram attention, the trigram transformer model, where whoever built that model had constrained their attention to only be 1 over the previous 2 or 3 tokens, and then they thought that this was a trigram model, but it actually was like information from beyond the last 3 tokens was getting infused into the current representation as you went up layer by layer. So this is the same reasoning that Ozzy was using. However, this reasoning does not apply here. This model, no matter how many layers it has, will always only be able to use information from the first 128 tokens. And to see that, you could draw out the attention and see that there's no way that any information from any other token can be included in this kind of setup. So thus you would expect Ozzy's attention model to get much, much higher perplexity than a standard transformer language model, because it has no context of the immediately preceding words. It only ever sees the first 128 tokens. Okay, so this question was, this part was also a little interesting. Here, Ozzy thought that perhaps he could implement his idea by just modifying the data instead of modifying the attention computation. So here, he just decided to create these truncated input sequences where the first 128 tokens are always the same for every prefix of the document. They're just the first 128 words. And then the next token is the current token, where I could be like position 5,000 of this document. You would get the 5,000th token and then try and predict the 5,001st token, conditioned on all of that. So the question is actually just asking why this is not equivalent to the formulation in 3.1. And the answer is because in this setup, your input actually includes x sub I. And so when you compute the query key dot product, you're not only computing it for the first 128 tokens, but you're also using the key vector for token x sub I. And this means that you actually have a lot more information than you do in the first case. Now you have the immediately preceding words identity. So at the very least, you have some sort of bigram connection going on here, which you don't have in the first case. And this is why this data modification implementation will yield a much lower perplexity than his original idea, because it's not only looking at the first 128 words, it's also looking at the current word, so the word immediately before the one you want to predict. All right, let's see here. Looks like this comment is about the previous question. The probability distribution for all the candidates is also not common, as they are individually classified and hence cannot be normalized by any standard method to form one single probability distribution. Yeah, that's true, I guess. We don't know about the calibration of this classifier. That is definitely a viable answer. So, because these are separate scores, you could normalize them using a softmax or something, but it's unclear how that would behave, especially in a decoding strategy involving like sampling or something. All right, the implementation mentioned in 3.2 would use the wrong positional embeddings. Wouldn't that result in higher perplexity? Yeah, so this is one thing that we thought about when writing this problem. So for x sub I, the position embedding is wrong, right? Because even if I is 5,000, this would get the position embedding of 129 or something like that. And so it's a little misleading. You don't know what gap there is between this I and this prefix. But for large values of I don't think this actually matters, because you have just the identity of this word, regardless of the position that it's at, is enough for the model to use it to predict the next word, since this is by far more useful for the current context than these 128 tokens. So since you're training this transformer from scratch, the model can learn to prioritize whatever's in position 129 of the input, regardless of whether that position embedding actually makes sense. So more generally, the ability to include this key vector in the computation significantly trumps the any sort of harm that is caused by having the wrong positional embedding. But you will receive partial credit for noting that the position embedding was wrong. All right, and finally, I'm not going to spend too much time on number 4 because there are many possible responses for this one. It was asking you to develop an evaluation metric that was like an automatic evaluation metric to evaluate long-form QA models trained on this ELI5 explain like I'm 5 data set. Hopefully, it would be better than Rouge. So some questions that you might have considered are, how correct is the answer? This is probably the hardest property to judge. You might have also wondered, how simple is the answer to understand? How fluent is the answer, like grammatically correct, and so on. So there are many different questions that you might have asked your annotators. You should have been specific with regard to how they would be allowed to respond, like what kind of rating scale would you make them give, and how would you train them, and so on. So this was a more open-ended problem. And the next part asked how you could train a model on the judgments that you collect to make a learn metric. So this could follow the models like BLERT and COMET that we talked about for machine translation evaluation. But whatever pre-trained model you selected, and the answer to this question kind of depends on the format of the judgments that you collect. So we will be grading this question kind of specific to each person's answer for 4.2. All right, so that was a midterm. Hopefully you have any misunderstandings are clarified now. If not, you can come to any of our office hours to discuss further. All of the TAs are familiar with all of the problems. All right, so let's get started with the topic of the day. We don't have that much time to cover it, so we'll just get through how much ever we can, and you can check out the previous year's lecture or just check out the slides on your own time for whatever we don't finish. Today we're talking about vision and language. So the intersection of understanding images and videos and also language. So there are many problems where this kind of thing is important. So image captioning is one task where you're given an image and asked to produce a natural language description of it. So this obviously has many applications, for people who can't see, or if you haven't put alt text on your images, or you just want some way of understanding what's going on in a large collection of images without actually looking through them. Maybe you can do some processing on these captions. There's also visual question answering. So we talked about question answering about passages like squad, but there's also visual question answering. So you can ask questions about this image, like, does the road look new, or what kind of tree is behind the truck? And you might want a system to be able to understand the question, understand the image, and spit out the correct answer. There are many other newer use cases which we won't discuss here, but recently OpenAI released this model called DALL-E 2, which, given any input text, will generate an image that corresponds to that. So you can say, like a cat floating in space drinking Coke, and it might generate an image of that. So these are newer applications that kind of are on the more creative side of things, where you can imagine them helping out artists and things like that. Okay, but we need to talk about some basics here. So we have throughout the semester discussed computing vector representations of words and sentences and paragraphs, but images are not formed by text, right? So how do we actually get to a point where we can compute vectors of images? So let's start with the simplest type of image, a grayscale image, which is just a grid of pixels where each pixel in a grayscale image takes a value from 0 to 255. And that value specifies the intensity of the grayness. So for a color image, it's basically the same, except you have 3 of these grids. You have they refer to channels, your RGB, red, green, and blue channels, and each of these you have the same like intensity of red, intensity of green, intensity of blue. So now you have this 3D representation of the image. It's a 3 by whatever the height and width of the image are. And this is a common representation for image processing today. So remember that when we're talking about text, our representation is usually, our input format is discrete words in a sequence, right? So we have this word order and word identity. Here we have pixel intensity values, and we have the grid in which they're arranged. Okay, so the main, I guess what used to be the main way of processing these images was via the convolution operator, and of course people still use this a lot today. At its core, the convolution is a very simple operation. So you define this small matrix, which is called a kernel or a filter. Here it's a 3 by 3 matrix, and you basically just slide it over your input image. So at this particular location in the image, I'm going to perform an element-wise multiplication, multiplying each value of the kernel with the corresponding element in the image. This is like for one channel of the image. And then I'm going to sum all of the products that I just computed, and I get a single number, and that number is going to be put in the center location of wherever this filter was centered in the image. And then I can just slide this filter over to the next position and compute the representation of this square, and so on. So by varying the values in this kernel, I can get a lot of different properties output in my output image. But first let's just go through an arithmetic example to make sure everyone understands. So here I have this input image, and this is my kernel. So it's 0 in all these locations, but 1 here and here. So if I'm at this particular window in the image and I want to apply the convolution using this kernel, I'm going to multiply 0 by 6, 0 by 7, 0 by 7, and finally I get a 1. 1 times 3 is 3. Everything else is 0 except here 1 times 1 is 1. And so I'm going to add up all those products. So all of them were 0 except 3 and 1. I get 4, and what goes into here is 4. So I wanted to show this demo because I think it's pretty intuitive in explaining the how the filter can affect things. So first, this is some like blurry picture of a guy's face. On the left, you can see the actual pixel values, and on the right, you can see what the corresponding grayscale representation of that pixel is. So here they say they're going to apply this 3 by 3 kernel to the image via convolution. And this one is going to do sharpening. So if you've used Photoshop ever, you probably know that there are many tools like sharpen or blur or whatever that, and you can implement lots of these things just with simple small kernels. So here, the sharpen kernel looks like it heavily upweights what is right in the center of the window, and either downweights or doesn't do anything to amplify anything else in this window. So basically you're going to, whatever is in the center is going to just be magnified here by a lot. So we can see what this actually does to the image. You can see that a lot of these grays became more like solid blacks, and a lot of the white, lighter parts became more white, and the edges became way more crisp. And you can kind of see the effect, right? If you look at this guy's eye here, originally it had a value of 53, and after applying the sharpened kernel, it was minus 164. So like it just became pure black. So we can change around what we want. If you wanted to use blur, for instance, so the opposite of sharpen, you can see what the blur kernel looks like. It has basically almost uniformly distributed probability over all of the values in this window, and you can see that instead of sharpening it, now this has become even more blurry. So there's many other things, like if you wanted the identity, which is be one in the center and 0 everywhere else. Yeah, so lots of interesting things you can do with just a simple 3x3 kernel. All right. So let's get back to this. So the convolutional neural net is a very popular way of learning representations of images. And essentially what it does is, instead of having fixed values in those kernels, like 5 in the center and 0 everywhere else, the convolutional neural network will learn the weights in those kernels. So this is very useful, of course, if you want to not hand specify how the model should understand an image. And as you stack more and more of these convolutional layers, the model will be able to essentially learn low-level features like edge detectors and things like that with certain filters, and then at the higher level of the network might be able to learn more things like object detectors and more semantic concepts. So yeah, that's basically the intuition. So here I'm passing this image through 4 different kernels, and I'm getting 4 different outputs that I can, do some pooling on, which would mean reducing the dimensionality of these this 4x224x224 tensor, or I could pass it through some more convolutions. I could just stack them. I could do so many things. So there's a concept called the stride in the convolutional operation, which refers to whether I shift my window down to every single pixel, or whether I skip some pixels when I do this. So if the stride is 2, I'm going to skip every other pixel when I'm shifting this kernel over the image. And so as such, I get an output which is half the size of the original image. So this could be useful if I wanted to downsample my image and reduce parameters or something like that. These pooling layers are another way to reduce the dimensionality of the output of each convolutional layer. So in a pooling layer, I'll take the output of, say, a convolutional layer, and I'll divide it into regions. And in each region, I might apply some simple function like take the max value in this region and preserve that and throw everything else away. So in this particular example, I downsample this 4x4 matrix to a 2x2 matrix by simply just taking the max value in each of the colored regions and throwing everything else away. This is useful to reduce the dimensionality of the representation and kind of force the model to learn only important things and not focus too much on features of the image that might not be salient to a particular task. Okay, so let's go through some history. Kind of the very first paper that got everyone hyped up about neural networks. This was more than 10 years ago now. Is informally referred to as AlexNet, named after the first author here. And this was basically a multi-layer convolutional neural network that was trained for the purpose of image classification. So given an image, there's some object in that image, like dog or house or truck or one of 1,000 different classes, and the network should predict what class that image belongs to. So this ImageNet dataset was 1.2 million images, which at this point you probably think, that's just not a lot of images at all, but back then it was a huge amount. This was one of the biggest data sets out there. And it classified an image into any of these categories. There are a lot of different dog breeds as part of this category set, or also cat types. So basically, the model would give you a softmax distribution over these 1,000 classes for any image input. And AlexNet looked like the following. So here you had your input image. You had a bunch of convolutional layers. These are the C's, followed by pooling layers. And then finally, once you got to the end of your convolution stack, you would pass the result into these linear layers, fully connected layers, which would eventually get you a vector of 1,000 dimensions, which you would softmax to get your final probability distribution. Okay, I see a question. I see a comment, go Canada. Yeah, go Canada. Is it possible to increase the dimensionality of the input instead of decreasing it? Yeah, this is possible. You can use something called a deconvolutional layer to do this. This was quite popular to generate different versions of images. Basically, you can have one set of convolutional layers that downsamples the image and into a bottleneck representation, and then stack some deconvolutional networks over it to, deconvolutional layers to increase the dimensionality of the input. Yeah, so very possible. Okay, so if you actually look and try and analyze what is happening at each of these convolutional layers, this is actually more informative than analyzing something like BERT for what is each attention head doing. Here you can actually see what these learned kernels are latching onto. So at the first layer, you have a lot of edge detectors that are getting activated by these like very low level edges. And then at a middle layer, you see like parts of faces here and there. And then at the top of the network, you see these are getting activated by like actual fully formed faces instead of just these pieces. So the network is definitely learning to go from low level at the low level features like edges and basic shapes and colors at the lowest level of the network to more abstract concepts by the top of the network. And of course, as we saw in NLP, more layers is usually better, and that happened first in vision. So in vision, like many years ago now, people were just scaling up these convolutional networks to bigger and bigger layers. The ResNet, the residual network, so remember in the transformer, there are these residual connections between every block. Those were originally developed for these convolutional networks to scale their depth better and improve the gradient flow in these kinds of networks. So there's a lot of connection between the advances in computer vision and what we see in NLP nowadays. I should also mention that it goes both ways. So nowadays, the most popular image representation models are not convolutional neural networks, but rather transformers. So transformers, originally developed for machine translation, are now being used in almost every state-of-the-art computer vision model to represent images. So it's kind of interesting to see how the fields influence each other. Okay, and not only is a bigger model better, but also more data is better. So we know this also from the ridiculous scale language models that we have these days. So here in this paper, they found that ImageNet pre-training is great, but you can also scale up to much bigger data sets by, for example, pre-training on Instagram. So you can give the model an Instagram image and ask it to predict like a tag of that image or something like that. And of course, this has been one way of getting training data, but now there's self-supervised objectives for vision, where you can imagine giving a network a patch from an image and asking whether or not this patch belongs in the missing part of the image or not. So there are all these cool contrastive learning objectives that people have developed to get rid of any sort of dependence on labeled data that are looking very promising. Okay, so this is obviously not a computer vision class, so I won't belabor the point, but if you're interested, there are many papers that you can check out, like the visual transformer paper and so on. At the end of the day, we have some way of passing an image through some neural network, whether it be a convolutional neural network or a CN or a transformer, and it gives us a vector that contains roughly the meaning of that image. So now, given that we have this, how can we use it to solve some of those tasks that we were talking about, like captioning or question answering? So just like in Elmo and Bert, where we were talking about transfer learning, where we have this pre-training task, which is more general, like just predict the next word or predict the mask word. And then we have our fine-tuning task, which is what we actually want to solve, like predict the sentiment of the sentence. Here it's kind of the same way. So we have a CNN, let's say, a convolutional neural network, that we train on the task of ImageNet classification. So this CNN we can then use for transfer learning. So even though it was originally trained for image classification, we can take this vector and repurpose it for some other task that we want. So we could, for example, use this vector for the purposes of visual cue question answering. A simple way to do that is to take the vector that we get after running a CNN over our image, so let's call this I, and we can run some sort of transformer or BERT or something over our question to get a question vector Q. And we can simply just concatenate both of these and feed it into a classifier, like a softmax classifier, to predict what the answer is. So visual question answering is often framed as a classification task, where you have like a couple thousand answers that are supposed to answer any sort of question, and your goal is to classify a question and image into one of those 2,000 answers. So this obviously isn't open-ended. I think more recently there are more complex visual QA datasets, but this is definitely one of the most established ones. Okay, so if I were in person here, I would ask the class to answer this question, but since I'm not, I will just do it myself. So this is not a good way of doing visual question answering, because the representation of the image is not contextualized with respect to the question. And similarly, the question representation is independently computed regardless of what the image is. So ideally, you would like to know what the question is before you process the image. So perhaps you can focus your representation of the image on whatever the salient attributes of that image are for answering this specific question. So as an example, let's look at this question. How many benches are shown? So here, if I wanted to compute a representation of this image, I ideally might just want it to focus on the bottom left corner, which has the benches, right? All this other stuff is extraneous for the question, but that wouldn't be happening in this setup here. So one thing that was developed to kind of contextualize the image with the question is called visual attention. This was inspired from the NLP concept of attention that was, again, originally developed for machine translation, which we went over in class. So here, we're going to first compute a representation of the question, and then we're going to divide the image into regions and score each region using our question representation. And ideally, this question representation would encourage our image model to focus only on the relevant part of the image. So let's say I run this question through BERT and I get this vector. Now I divide this image into some regions in a grid. This is the most common way to do it. And basically for each of these squares, you're going to compute a separate vector, and then you're going to compute basically the equivalent of this query key dot product that we talked about in attention. Here the query is the question vector, and the keys are all of the vectors associated with the regions here, which you naturally get from a convolutional neural network. And then you take the weighted average of all of the key vectors using the attention scores. So you can see in this ideal case, almost all the attention was concentrated around these 4 boxes, and this whole part of the image had no attention on it. So it doesn't impact the representation as much. This is similar to Realm. Kind of, I would say it's more similar to just a standard attention mechanism, except the source of the keys is not text, but it is instead these regions of images. Okay, and once you have computed your weighted average of these region representations, you can feed that into a softmax layer to predict the answer. All right. There is also a version of attention proposed that instead of doing soft averaging, this like weighted sum of all the boxes using the attention scores, instead chose just a single box to focus on and ignore all the other boxes. So this is tricky to do because it's like a discrete choice, right? You're choosing one box and there's no gradient flow over any of the other boxes. Oh, this should be a 0, not a 0.5. You can ignore that. So you need to use other learning strategies to accomplish this, and reinforcement learning is one way to do it. But these kind of hard attention strategies are not as popular as the much simpler soft attention, which can be trained easily through gradient descent. All right. So we talked about these kinds of questions about natural images, but we might also be interested in whether models can have any sort of spatial understanding and whether they can perform spatial reasoning. This is something, of course, that humans can easily do, and it would be nice if our models could, for example, answer, is there a red shape above a circle in this image? So here's a circle, and here's a red shape, so yes, this is true. But it's kind of hard for a computer unless it has a good understanding of the position and attributes of all these different objects. So to do this, you basically need first, for every concept in the question, you need to have some understanding of it. So you need to know roughly what is a circle, and you need to know what is red and what does above mean. And then you need another approach that can kind of compose these different operations. So you know what a circle means and you know what above means. So can you, kind of learn what above a circle, this specific operation means? So this might involve chaining together different modules that understand single concepts. So if I have a module for circle, maybe I have a circle detector, and I have a module for red, which is basically, it goes over the image and tells me if any object is red. Now I have this more complex above relation, which takes in two regions of the image and asks if one is above the other or not. So this concept of neural module networks, which were developed by Jacob Andreas, kind of learn both these individual modules of different concepts as well as how to structure them together to get answers to these kinds of complex questions. So you can see here, is there a red shape above a circle? I have a different module. These are these individual Legos for, is something red? Does it exist? Is it above something? And so on. Each of these modules is implemented with its own separate neural network over the image. And then I'm going to basically make a tree of these modules. So given a question, I can develop a tree, like, does there exist a red shape above a circle or something like that, that when chained together in this way will give me the right answer. And then I can train the module parameters using some training data. It's harder to train the tree, the parser, which gives you this tree structure from the question, but you can also do that as well using like reinforcement learning. So here, this tree would look like, first I have the exist module, but to get there I need to feed in all these low-level things like red, circle above, and exists, and so on. So those were all on synthetic images originally, but there are more recent data sets that port this over to natural images. So here I have, in this NLVR squared data set, each example is two images. And you have one image on the left, one on the right, and then you have a statement, and you're simply asked whether the statement is true and false. But these statements can be very complicated. So here we see the left image contains twice the number of dogs as the right image, so that's true. This has 2 dogs, this has 1 dog, and at least 2 dogs in total are standing. We see 3 dogs are standing, so this is true. But like, this involves a lot of complex reasoning between the relationships between both of these images, as well as reasoning about both of the images in total. So it's quite a hard data set, and for a long time the performance on this data set was basically at random, although recently it's gotten much better. Okay, so you can also go further in the space of vision and language. Like, you can actually learn agents that exist in some sort of visual environment, so like a video game, for example, and you can instruct them on how to behave in that network, so in that environment. So in this serial bar data set, there's it's essentially a game where there's an agent in this virtual environment who's asked to pick up various cards, and they don't know where the cards are, so they need to get an instruction from someone. So usually the agents here are computer agents, and they receive commands in natural language, like pick up the yellow hearts and run past me towards the bush sticking out and then get these 3 green stars on the opposite side. So you can train these agents to follow natural language commands within the visual environment. This is very cool for like navigation of computer agents. There are cooler versions of this that are put in, for example, Google Street View. So you can try and like instruct some sort of agent to travel to somewhere based on landmarks in Google Street View. There's lots of very interesting things that are happening in this space. Okay, so I wanted to go into a little detail about text generation conditioned on images. So image captioning is like the canonical example of this kind of thing, where you have an image and you feed that image representation into some sort of language model to generate the caption. So this was from the one of the very first working image captioning systems. And now this might seem like not very impressive to you, but when it came out in like 2014, 2015, it was just shocking to see that you could make a language model connected to an image and have it generate text with no external features or any human design thing in the loop. So how this whole process worked is that you get an image and you pass it into your pre-trained convolutional neural network. So this could be one trained on ImageNet. You see the transfer learning here. Then you extract this layer, this 4096 dimensional representation of the image, and you are going to consider that your representation of this image. So similar to if you were to take some text, pass it into BERT, and then extract the CLS token as the representation of that text. Here, this was BERT for images, basically. It came much before BERT, but you pass your image through a pre-trained CNN and extract a representation from the final-ish layer as a feature representation of that image. So now, given that vector, you're going to basically, and these image captioning models were originally built with recurrent neural networks, not transformers. So you would initialize the hidden state of the RNN with this vector that you get from the image, and then you would just train it as a language model to generate the text. So very simple. You feed in the start token, you apply the softmax over the hidden state, you sample through some process, right? You could do nucleus sampling, or you could do greedy decoding or whatever, and just proceed like that. So it should be kind of interesting that, we can understand models like these, even though they're using 2 different modalities, text and vision, without any special knowledge, right? We've already know all the models and objective functions and so on to generate the text. We're just, instead of conditioning on a vector representation of input text, we're now just replacing that with a vector of an image. So yeah, you can see some failure cases of these initial examples. So a woman is holding a cat in her hand. She is not, but maybe her code fooled the model. Or a person holding a computer mouse on a desk. This is a phone, not a mouse. This person is catching a ball, not throwing a ball. So you can see that these initial systems didn't really understand the content of the images. They were mainly seeing like, oh, this is a baseball player, let me spit out something about baseball. Or a bird is perched on a tree branch. This is not a bird, but yeah. And after this, people started applying attention mechanisms in this image captioning concept. So you would have not only just this vector, but you might have an attention weighted average of those region vectors at each time step. And so here you could actually kind of see where in the image the model was looking at when it produced a certain word. So if you look at this one, this bird flying over some water, you have a bird flying over a body of water. And when it generates the word bird, you can see that its attention, this white thing, is focused on the bird. When it generates body of water, it seems to be distributed over the water. There are other good examples, like a stop sign is on a road. When you're producing stop, it's focusing on the stop sign. A dog is standing on the hardwood floor, and so on. But in general, these attention maps were hard to interpret. It turned out that a lot of the time the model would just always put the attention in the center of the image, because that's usually where whatever important was happening was located. Then more recently, after things like Elmo and BERT came out, there started to be vision and language pre-training. So you can do something like BERT with both visual inputs as well as language inputs. So there's many different models. This Vilbert is just one of them. So you can imagine masking out a region of the image and asking the model to predict whatever goes in there. And finally, there's OpenAI's CLIP, which is a very large-scale retriever-style model where they collected 400 million image and text pairs from the internet, and then just simply trained an image encoder and a text encoder with this contrastive loss function. So given a collection of images and text, predict which of the image text pairs actually occurred in this data set and which are negative examples. And by doing this, they had really powerful image embeddings and text embeddings. And their more recent work on DALL-E allows you to generate images conditioned on text. So maybe we'll look at some of those next week. But they're very impressive. Okay, and this is just how CLIP works. So you have an image of, say, a dog. This is a batch of images, so you have many images. The dog is just the first one, I1. And similarly, you have lots of different text examples. So some of these are the right pairs. So I1 and T1 here. This is a picture of Pepper, the Aussie pup. But you can see that I1 paired with T2, T2 is a negative. So whatever is on the diagonal here, these are the positive examples that should be, these dot products should be scored high, and then all of the other cells here should be scored low. So with this very simple objective function, they were able to train a very powerful image encoder and text encoder. Pretty cool model here. Can we say that the attention maps are attempting to segment the image? I mean, they are showing you which parts of the image contribute more to the representation at that particular token, if you're talking about the image captioning case. So ideally the attention maps could be so detailed that you could actually infer segmentation from them, but in practice they are not. It depends on first of all the strategy used to break it into regions, but oftentimes those regions are too coarse and they're boxes, right? So you're limited in capturing, like curved edges and so on. Okay, so let's take a look at some stuff from CLIP. So CLIP showed that you don't really need to train on a labeled data set like ImageNet to get good understanding of language and images. It's good at, even like if you have a sketch of a banana, it can detect that this is a banana and not like something else, which a normal classifier would do. If you have like a cut up banana, So it can also detect that these are bananas, even though they're maybe a little out of distribution for an ImageNet model. Yeah, so it's much more robust, I guess is the conclusion, than these previous ImageNet trained models. All right, so that's all I had for today. Next week, I think Monday is a holiday, and we'll continue our class on Wednesday, and I think I'll be back in person by then. I probably could have come back today. So anyway, see you then.